reoccurring topic that people seem to be talking about is driver thickness. Right? The material of a planar magnetic diaphragm is what we're going to be talking about for the most part, and how the thickness affects the sound, the performance. How much does it matter? So for a while, there's been a bit of a race to the bottom, so to say, to try to make the diaphragm as thin as possible, because everyone thinks, well, surely that makes a better headphone. The thinner, the better. I want this thing to be 1 atom thick.
Now, let's just say that we should state that we kind of stayed out of that race. We have really thin material, and we don't specify what that is. But there were others racing on that one.
Okay.
Yeah, we were kind of out of it, but there was a race.
But in general, there were a handful of companies that...
the word nano
Yeah.
started popping up in front of thicknesses.
Right.
Yes,
It was-
nanometer.
for a while, it was good
Yeah.
marketing, I
Yeah,
suppose, right?
I
It
guess
helped
nobody
push.
really does that anymore.
No.
It kind of stopped.
Yeah. Well, the reality of it is it was irrelevant to the end user. It was basically how does it sound, right?
And that's the silly thing, right? When this was happening, you look at what people were saying about the sound between these different products, and of course, inevitably, there was a handful of people that owned various generations before this thickness war started and after. And you really didn't see a whole lot of people saying, wow, I couldn't imagine something could improve so much. This is vastly superior in every way. You didn't see a whole lot of that. In general, people are just like, it's a good headphone, but
Yeah.
it's not like some crazy radical change.
And the reason for that is because other factors are involved. It's not just about thickness. If it was
Right.
that simple, we'd all just go thin and call it a day until we were down to an atom thick, right? Which now I guess that's the new thing now. People are doing atom thick coatings and
Yeah,
you
that's
know,
common. That's actually
carbon
very, very
this
common.
And which I mean, again, it's
Well, that is
true.
part of it. I mean, it's not just the physical driver material; it's also the trace and whatnot, thickness and
Yeah.
everything. So
Yeah, there's a
Well,
lot involved.
The trouble is we live in a world where things can be very, very difficult to do at times. So unfortunately, if things are very, very difficult to do, usually you run into a lot of variants, a lot of issues. And this usually presents itself as comparatively worse quality than you would get for something that's easy. And now I think this requires clarification, so I'll expand on that.
Oh no,
There's a bit of discussion here. All right, calm down.
is this lions and tigers and bears?
Yes. You have two sides of the equation here, right? You have the thinnest diaphragm that you could physically manufacture, and that's light. So you think, okay, it's easier for it to start, stop, move. It's easier for it to closely mimic the input waveform. So your
Low
music,
mass.
right, it moves faster. So it plays your music closer to how it's supposed to. Supposedly,
Theoretically.
allegedly, right? And on the other side, you have a really, really heavy driver, thick, sturdy. It has no issues, appreciably, with the diaphragm moving non-linearly. Like it doesn't wrinkle or roll or flex or crinkle. It doesn't have any of these issues.
When it's told to move, the whole thing moves.
The whole thing
evenly.
moves perfectly because it's a dump truck,
Like a
right?
sheet of steel.
1 inch thick of steel plate, right? There's
they
no
used
issue.
to do that
Yeah,
actually.
steel drivers.
Yeah, and headphones. We're
Did
talking
they?
like 1923.
1 inch thick steel plate.
Not 1
Well,
inch
not
thick,
1 inch.
but
That had to be
thin
brutal.
steel. But yeah,
Get out.
Yeah.
I didn't even know that. Well, I could see why you don't see any of those anywhere.
no.
That would be.
So expanding on this idea,
Yeah.
you have these two
drop the
sides.
thing and the cone just rips right out.
No, you just take them up. They're just a little thin steel disc. And
Oh.
Oh boy.
Oh, jeez.
So you have your 1 atom thick
That's-
driver,
also
right?
a flat driver.
Oh Jesus.
Yeah.
I got to see a picture of that. We got to pull up a picture.
I think
I've
we
never.
had- I think we no.
No, I've never. Oh, I know what you mean. Oh, you mean the old carbon style
Yeah, like
drivers
phones
that used
did
to put in
that too.
phone
Yeah.
in phone sets.
Yeah.
I didn't even know. I'm not sure if those are steel, but maybe there was a thin plate of
Yeah.
something and it was flat.
Very
No,
rigid.
That's metallized something.
Yeah. It was kind of like a darker bluish color. I might have been anodized. I don't remember. Anyway, we'll look that up. We'll figure it out. We'll put it in the notes. But yeah, the old carbon receiver.
Yeah, but
things
I mean,
in
we
phone
had
set,
a,
ear
Jerry
sets,
had 'em.
telephones, old telephones. Yeah,
Headphones that had a plate.
yeah.
They're really old.
No, I got a set that's like that. It might be like that too.
We'll have to look.
Yeah. we'll have to look.
Add some
Anyway,
B-roll of them.
anyway,
Beautiful.
What were you going to say?
Anyways, so you have two sides of the equation, right? You have your 1 atom thick driver, amazingly thin, about as light as mass as possible. The other side, you got your inch thick steel plate, dump truck, super rigid, no real issues other than accelerating this huge mass. Both sides present challenges. The super lightweight thin one, very, very fragile, very difficult to deal with, mount, tension, difficult to get a trace pattern on it. And now the trace pattern has actually comparatively huge mass which presents other challenges because now you have this huge mass of trace, which is where the force is actually being parted.
That's kind of like gluing
That's
a
what's
wire
pushing
to
and pulling.
nothing.
Right. It's
like
gluing a wire to
it's
incredibly
like
thin film.
Think of taking a piece of tissue paper, like a toilet paper, and then putting a wire on it and gluing it and saying, "Okay, drive."
Yeah,
Somehow
that's kind of how
you're
early
running into
planers were.
you're running into some real delicacy issues there.
Well, all
They
the
used to do
forces
that.
are on this trace. And so you're moving this incredibly thin membrane from just this wire glued on it. So obviously in between it, it's going to wrinkle, distort, flex. It's going to have all kinds of issues.
Right, it lacks rigidity.
Right. And now your 1-inch steel plate trace is meaningless compared to that. No issues at all. You move that wire, the whole thing's moving as comparatively dead perfect.
Yeah, it can't twist or
Right.
torque or anything.
So you see the issues on both sides. Now, one would imagine somewhere in the middle is where you want to be. Obviously, both are a little ridiculous. They both don't really work practically. The
Quite
atom
extreme,
thick,
yes.
you look at it and it's going to pop a hole through it. And the steel plate, well, that's ridiculous, right? It's way, way, way too heavy. It'll be terrible. But there's always an optimal thickness, and that's the trouble.
Well, I think in audio, you'll look at it as it's kind of like in a lot of things too, psychology and stuff. They kind of look at things on a bell curve, where it goes up, it peaks, and it goes back down, and you want to be up here somewhere.
Yeah,
the mean,
ideally.
the average, and you kind of got to look at it that way, where you could go thin, and you reach a point where for that particular driver, that's right where you want to be, and you keep going thinner. Now it goes down the hill, it goes the other way, and that goes for any of the drivers. It goes for any of them. Dynamic, electrostat, it's all the same thing.
But there's more factors than just the driver thickness.
Right.
Is the real takeaway here.
Yeah, right.
Yeah.
Driver thickness is actually a very small portion of the equation.
Yeah.
Really how the driver works, how it's designed, the magnet structure and whatnot, the acoustic impedance present on this, whether or not it's closely coupled to your head, whether or not it's an enclosed chamber and whatnot. All these things make a big difference on what driver you need. There really is no one size fits all. So for some people, maybe a thinner driver is better. But comparing the thickness of the diaphragm really isn't a useful metric.
Well, it's kind of like looking at, how electrostats tend to be noted for not really doing the lower end bass real well. And there's reasons for that, right? I mean,
Well, yeah.
they probably need to use like the thinnest material you could find because the electrostatic force is weak relative to
Big
an
heavy magnets.
electrodynamic. Yeah, it can only move, it only has so much power. I mean, these drivers are basically, in technical terms, they're called motors, right? They're a motor structure. You have a coil, you run
Yeah.
current through it, and you create motion.
Same
It's
concept.
not that different than spinning a motor, but this way it's a linear motion. So they're motors. So think about how a motor works, right? More power in, more power out type thing, more torque, and it's the same deal with this. Watts in produce acoustic pressure out, and little milliwatts in produce much less acoustic pressure out. So
Well, yeah.
mass is one of the things. The heavier it is, the more you got to push it, the more power you need. But by the same token, lighter items, you push it too hard and they fall apart. They break up. You sound like shit. So you could kind of see where there's trade-offs in either direction.
Unfortunately, most of the design is really just overcoming the combination of limitations you have presented to you, right? You always have the reality of the situation. It always needs to be physically made. And there's difficulties with all different sides. It needs to be a certain price. It needs to look a certain way. It needs to fit in a certain enclosure. It needs to do certain things. And there's only a finite number of ways to achieve it. And sometimes you come up with a really innovative solution that nobody's ever done before, but all that typically does is expand the envelope a little bit of how you could get your job done. You still have realities. And so it's still, best we know, near impossible to make an amazing driver, one atom thick.
Yeah.
Well, maybe you can make one. It's like a lab experiment.
It would be incredibly challenging to have
It would
anything
play
like
music
that.
for 30 seconds and then fall apart.
It would have to be made out of some incredibly, incredibly strong, rigid material for it to not just break at any type of gentle waft across
And
it.
even then, what would it sound like? Because you don't know till you try
Is
it.
it necessarily better?
Yeah, right, exactly.
Yeah.
Chances are it won't. Chances are it won't perform the way you would think it would.
Well, chances are it wouldn't matter because you couldn't actually manufacture it.
Well, that's true.
You know?
But even if you could make one, you see that all the time, like in science, in the R&D side, and especially in colleges and stuff, where they're always trying to come up with new materials,
Yeah.
new this, new that. And you see reports of how they made this, and I've been watching this for years because we're always looking for new materials ourselves. And invariably, they'll come up with something, and they'll probably apply for a patent, and the college owns the rights to it.
The reality is we live in the real world. There's always limitations. There's advantages and disadvantages to both sides. So the best approach for you is going to be dependent on your design.
And so anyway, invariably, these colleges are always, writing these papers going, look what we did, we're the first to do this, and it does this, and, it's an amazing this, it's a material, and when you hit it with photons, it produces electricity, right? So it's like, wow, look at, so there's always, after that, usually at the end, there's a forward-looking statement like, just think of the possibilities.
You see that a lot with solar cells. Yeah. Everyone's always saying, look at this research paper showing 99.99% efficiency. Yeah. And everyone expects in 6 months we're going to see this amazing break.
It never happens because to make that a commercial reality is the hardest part.
Right.
It's that leap of thing that I talked about where you got a crystal ball. Okay, you see where you want to be, right? But it takes you 20 years to get there because, okay, we did this once in a lab in this tiny Petri dish. Now how do we make this worldwide? And it's all of a sudden you can't.
For almost every industry, that's exactly the way these things are. It's a bit more prevalent in some of the others, but there's always something that can be done theoretically, but nobody knows how to really make it manufacturable. It's so expensive and difficult to do. Right. It's just not practical.
Yeah, they probably spent tens of millions of dollars to get to the one.
Right. Yeah. And so how do you make it reliable? How do you make it repeatable?
Right. Well, we can't do that yet.
Yeah, I've seen a few things like that, materials that have come out, and now it's been like 5 or 6 years later, and there's still nothing.
Yeah, because we're kind of following up on it, going, oh, that looks promising. We might be able to use that. It never happens. Yeah. Just for whatever reason. The chances are it's money. I mean,
that's
someone realizes that they're going to need a shit ton of investors to deal with this. And in the end, are you going to make anything on it? Is it really...
Well, that's the thing.
Where is its value in the world?
A specific application usually. It's like, well, it could be used for this. It could be used for this. So.
Yeah, it just has this amazing feature, but they haven't quite figured out what to do with it yet.
Yeah, and you can't make it.
You can't. By the way, we can't make it yet.
And you're not out advertising it or anything. Oh, we have a new process for you. So if someone has to stumble upon it and be
this stuff is cool. Yeah. I mean, it's cool, and especially at a college level, it's great because think about these undergrad students are learning a shit ton about making things. Which is ultimately what we do, what we should be doing. That's what we do in the U.S. That's what we should do. We make things. We should be making things, more things. So it's great, but you gotta. I think somewhere you got to think about practicality.
Yeah, well,
and not in the end. Maybe you should start thinking about it at the beginning. But then again,
you
that
never
would
really
stifle,
know, though, right?
That would stifle it.
Stifles innovation.
Yeah, right.
Well, as Elon said, it's like the design is easy, the manufacturing is hard.
Yeah, there's no question.
And for some reason, consumers are so out of touch with that. They don't understand.
Yeah.
It is more often than not much, much easier to design something than it is to actually make it.
Well, I think that's the problem.
Making it is hard.
Right. I think that's the problem. I think most consumers don't make things.
Right.
They are consumers. They buy things that are already made for them. And that's an answer to a lot of people that I see, and a lot of bitches I see on forums and so on with all of the industries. Like, well, did you ever try making this before? And then you would start to realize why it's made the way it is, right? Because you can't make it the way you think it should be. It can't happen. It sounds great on paper.
Theory's easy, yeah.
It sounds great on paper. And we've probably already tried it 20 different ways to sundown. And in the end, the way it's made is the way it can be made. That happens a lot. And granted, there's a lot of things that can be improved.
Oh, absolutely. You could always improve almost everything.
Yeah, sure.
I entirely agree with the fact that almost every product has a huge number of flaws and almost every design is wrong.
Right.
But
until
some
you try
are
to
less
make it.
wrong than others.
Yeah.
Right?
Right.
There's always a way to improve almost everything.
There is. There is. And then you got to make it.
Well, the other thing is sometimes the solutions are you overthink the solutions. They're way easier, and you're like, man, we're going way too complicated on this.
Yeah.
The easiest solution is usually the best.
Usually.
Yeah. Usually.
And it's very hard to make things very simple.
Simpler is better.
And work, that is.
Yeah.
Simple and work.
Yeah. That's kind of been something we've always worked on, though, is we always try to keep it as simple as possible, to try to have one part do more than one job. Otherwise, you just have a bunch of parts. Adds to weight, adds to complexity.
It's easier to just bolt parts on that do discrete jobs.
Yeah, like Legos, you just keep stacking it onto you.
Yeah.
Get to what you want, the shape you want.
It doesn't end up with a good product a lot of times, though.
No.
Maybe there's some applications where you want it to be modular and serviceable, but it adds cost and complexity a lot of times, and it's not usually desirable.
We have our B gnome here. Well, he's our foam gnome right now.
Foam
He's got the inside of a Diana ear pad, which we've been working on for a while, on a new design, which we just started shipping a few months ago. But anyway, he's our bee gnome, and yeah, he makes honey.
Oh,
Yeah,
does he know?
yeah. I don't think we ever tried honey on a driver before.
I don't think you want it.
Probably would attract bees and flies and insects. So.
Definitely.
Yeah, but it would add mass. We could put on really thin.
Mass loading your drivers.
If you heat it, will it dry? All right, we don't want to use honey. All right, but it's his idea because then it perpetuates the species. You need more of him to get the more honey to make drivers. So. Anyway, on that note, if you made it to the end here, obviously we're losing it.
Yeah.
So join us. Thank you for joining us. Thanks for watching, everybody. Thumbs us up if you like this. Take care of yourselves.